to the classification models. Actually, we took a look to the very first one, which is the logistics regression. Nevertheless, today we will take a look to two other, actually three other remaining models for classification. And in order to cover some other approaches to try to, not to try, to focus into how to, when we have a universe of data, how we can create different groups in order to, based on the different skills, different capabilities, different background, and different um, characteristics of each one of the groups, how can we, a new input, how can we classify it? So today we will take a look to mainly two main models, but we will take a look to a third one that it's nothing but it's a complementary model for all of them. The first one and the most common is the nearest neighbors. The nearest neighbors is nothing but if um, you have certain amount of transactions and you would like to identify a threshold, no matter how thin, no matter how thick the threshold it is, you can establish thresholds and classify to particular a binary classification or any type of classification based on this particular model. And the other one, which is nearest neighbor. In other words, it identifies the how close all the models, all the different transactions are, establish what are the main classification for them, and afterward creates a particular vector that divides them all into two different groups. And the other one is a support vector machine. The support vector machine is nothing but a four dimensions vector that no matter how you have your data distributed across, that vector would be able to classify the all the data, no matter what, into two main groups. So, talking about the different models for the nearest neighbors, we will take a look about how to create the observation samples. We will create the feature scaling. As you may be aware, the feature scaling, we have already done it in other models. We will understand the Euclidean distance, and actually superficially, we already took a look to that in the linear regression. If you remember the distance between 2 points, that's the Euclidean distance, which is the comparison between x1 and x2 and y1 and y2. But we will discuss it today a little bit further, and also how to declare the distance function, because at the end of the day, this distance function provides what's the um between 2 points, what's the distance between those 2 points, and also what's the relationship between that point and other points. And super vector machine is nothing but a vector, three-dimensional vector takes place into a universe of data, and that vector will divide our data into two or more groups, depending upon how we would like to classify them. Because a classification, if you remember, actually, instead of saying myself, I'll ask around. So, Andrea, do you remember that we mentioned about classification and I used several examples? Can you please remind me one of the examples that we used?
You mean classifications from, I'm sorry, I just moved out from the computer. I couldn't hear your whole question, but do you mean
Yeah, so
classifications of um indirect indirect data?
yeah, do you remember that I mentioned several examples about classification? One of them that I mentioned about, do you remember one of them? Like, I don't know, I gave several examples. But talking about classification, top of mind, which example can you use to explain classification?
Um, Numeric and characteristics, like when we were classifying the salaries, they were classified by age and experience, etc. I'm not sure if that's what you mean.
That's one of the examples, like for instance, but that one was the logistics regression. But if you remember, we talked about, for instance, how to classify animals. Do you remember that I mentioned animals as part of the classifications, and also I mentioned some other examples, but the main one that I used, do you remember animals? And what were the classifications that I mentioned?
No, I'm sorry, I do not.
That's fine. Anyone who does actually remember what were the examples that I used in order to classify animals?
Yeah, it was the one with Mickey Mouse and Donald, wasn't it?
Yeah, yeah, that's one of the examples. But if you remember, that was example that I used in the presentation.
You
But do you
mean like the
remember?
fishes
Yeah,
that
that one.
they had like same type of color and like a tail, etc.
Yeah,
Size.
beautiful. That's one of the examples that I used in the presentation. But also, anyone who may think of what other way that you can classify animals in general, what are the main
Mam
groups?
You also,
Mammals,
we have mammal,
reptiles.
Mammals.
reptiles,
Beautiful.
amphibians.
Exactly. Exactly. So imagine that you have a universe of animals. And I may say not only five or 10. Let's say they have millions of animals. And someone asks you, please classify them. Can you do it kind of in a short period without requiring an algorithm? I mean, maybe it's gonna take you a while, right? It actually would take me a while. Sorry. In case I had, I don't know, a million of animals and just ask me, classify them. There'll be some point where you get very tired, right? Taking one by one and saying, you know what, this one it's maybe what if you get I don't know, what if you get a weird animal like um
Platypus.
like best. Yeah, that one is kind of those are I mean those in Australia or in Oceania, those are the weirdest animals that if they ask you to classify them, right? It will be totally weird. So, anyways, these algorithms most probably will do it wrong as well, because if you do a platypus, most probably it will think the algorithm may think that it's a duck, maybe. Most probably, top of mind, right?
Mm.
How it's everyone aware of what a platypus it is all about, which is
Yeah,
big part?
but that wouldn't be
Yeah,
like an outliner or the
most
bloody
most probably can be an outlier. Why not?
outlier.
Because at the end of the day, but I anticipate that top of mind, but maybe due to the tail could be an outlier. Far part of that, if I were the algorithm, would classify it as a duck, honestly, as a bird, maybe, most probably. Nevertheless, you can also train the model to say, you know what, that outlier is not exactly an outlier. You can see the algorithm. That's another classification that only happens in freaking Australia, right? And some other animals may be pretty much alike, or the platypus. That's the case of the platypus. But anyways, so at the end of the day, yes, I anticipate that that thing would be pretty much an outlier. Oh, the axolotl. Yeah, the axolotl could be another good example. How would you classify that thing, right? It's a fish? No, it's a reptile. Maybe. Actually, not. Right? It's another animal. But again, those are outliers, and it may happen everywhere. At the end of the day, it's. But let's say that if you have a universe of animals, you would focus only into those outliers to analyze perhaps a 5, 10, 20 transactions that you may think of that you know what it requires more detail. Nevertheless, the other million most probably would be able to be classified using these models, which is the great thing. So again, at the end of the day, these models are expected to help you to take decisions, but at the end of the day, would help you to identify which ones require more priority for a human being and more focus for a human being rather than in the remaining ones that actually are easier can be done by an algorithm. something that it's the great thing about this. You will only focus to something that is highly important and highly risky and highly its importance, risk, and priority are the three things that you would need to focus as a human being, as an expert. The remaining ones can be taken care of by the algorithm. So that's the great thing about this. So for today, we'll take a look, as I told you, to nearest neighbors and support vector machine. The nearest neighbors, again, takes into consideration how close are two elements one to each other, how far are two elements one to each other, and based on the different skills and the different characteristics of those algorithms, will classify them into right or wrong, into one group or the other, and so on and so forth. We will learn how to identify the different neighbors and distance metrics. We will develop how to implement the KNN for real-world data sets and give an interpretation to those. And also recognize the advantages of you and limitations of nearest neighbors. Because sometimes, and some of you I already told you that classification is one thing. However, clustering goes above and beyond that. That would help you to identify even deeper groups, even more details about those groups. Remember, we are going to from general to specific in this class. And now, rather than linear regression or a binary regression, here's taking into consideration other factors to classify them. And last but not least, okay, let's focus in the next targets, which are related to support vector machine. Comprehend the fundamentals for support vector machine. Understand a hyperplane, the margin, and how SVM maximizes the separation between classes, between two classes. You'll learn how to select the kernel functions, which are linear, polynomial, and RBF, to handle non-linear separable data. Because if you remember, last class we saw the logistics regression, which is a very, very linear separation. This one, it's rather than a linear, it's a plane that would help you to split between the data. Previous last, it will be recognize the strengths of SVM and high dimensional spaces and the applications of different datasets for classification. And also, you'll focus into identify the different levels that are tailored for this particular classification model. So let me give you, this is kind of the logic behind the scenes. Like, for instance, this is kind of the decision tree in the sense that you have different observations, right? You organize them, and afterward, you go one by one and take the first samples. Once that you take the samples, you identify, if you remember, what's the percentage of samples that we need to take? One volunteer? At top, at most.
30%.
40%.
40%. You are learning it pretty well, exactly. At most 40% to avoid what? Does anyone remember when we are performing the
Overfitting.
sample?
Overfitting.
Overfitting. Beautiful. Who was it? Enrique? It was you? Was that so?
No, I said
Okay. Thank you so much. Yeah, exactly. It's to avoid overfitting. And what does overfitting is all about?
Forcing the data to behave in a certain way.
Beautiful. Exactly. Like we want the model to learn, not to force to behave in some certain fashion, right? We don't want to align all the objects into the same group. We want the algorithm to understand what's going on and describe the data, not to force the data to behave in same fashion. Beautiful. All of you are amazing. That's a wonderful answer. So it's exactly what we're doing here. So we take a sample, and afterward, we analyze one by one to understand what's the behavior. It takes the full data set, establishes the sample size. In this case, we said at most 40%. It takes the random values out of that 40% and understands what's the different skills of each and one of the data points. And afterward, for the upcoming one, asks the same questions. Do you have these characteristics? First one, second, third, fourth, and so on and so forth. And if it matches, we'll classify it. Else, it would be an error, an outlier, or something else, or out of a norm. right? That's pretty much the process that it takes place. And this is kind of a visual example about a decision tree. This is a decision tree where it takes one by one and it identifies where do you match. Okay, you match in the first one, beautiful. You've matched in the second one, beautiful. You match in the third one, guess what? You're part of the group. And it goes one by one to it. You belong to the first one? No, it doesn't. Do you belong to the second one? Amazing. Now, do you belong into the subs division? Do you belong to the first or the second group? And so on and so forth. Depending upon what's the weight of the different skills and capabilities for that particular sample, it identifies what group it belongs to and classifies it. That's the way it works. When we are talking about feature scaling, actually I have explained it. Who would like to be the adventurous person to explain what does feature scaling stand for? Or what is that being used for?
So when you
I
normalize your data,
Amazing. Exactly. Pretty much you create a threshold based on the space that you have available. And by space, I mean it can be a chart, it can be a canvas, or it can be also two groups, right? So based on feature scaling, you say, you know what, the maximum limit, or which is the maximum value that you have in your sample, is X, right? Or I'm sorry, X now. It would be certain the extreme limit value of the entire data set and the minimum value. So based on maximum and minimum values, it establishes limits, right? Between them, it says, you know what? If those are a million records, you cannot chart a million records in a million of kilometers. It wouldn't be feasible. It wouldn't be actually not even in 100 meters, right? It's very difficult to visualize that. So what it does, it creates a scale, which would be I use one analogy out of that. What would be the analogy for a feature scaling? Do you remember the map? Do you remember that I mentioned the maps? That it has a scale at the bottom or at the top. When you're taking out to a map, no matter how big or what it belongs to, for instance, let's take a look a world map. Usually it has a scale, 1 to 10 million, 1 to a million, one that's feature scaling, which means something that is very big, it gives a scale that can be visualized in a canvas, and it's something that is more visible or it's easy to digest for someone for an eyesight. Simply sight, you can identify no matter what scale it has, no matter what's a million, 10 millions, I don't know, you name it, a trillion or whatever, you can see it into a scale. Also, that scaling can be a binary scale. Either is correct or no, whether it pass or no. If you remember, the logistics regression was pretty much that. Does it pass? Does it or it doesn't pass? Does it achieve the goal or it doesn't? Right? It's a binary decision. That's a feature scaling. In other words, you establish the thresholds, and based on those thresholds, you plot and visualize your data in that particular scale. That's feature scaling. You establish the rules, the limit, and based on those rules and limits, you can plot and visualize your data and try to identify it into a visual canvas. Crystal clear for everyone? Crystal clear? Does anyone has any question about it? Questions? Concerns? Okay. So in other words, it's comparing data in different units into something more visible and visual for all of us. Go for it, Enrique.
Just one question. You mentioned last time that for regression we don't need feature scaling, right? And for classification we don't need
That's
it.
a very good question. For regression, the feature scaling is being done automatically by the code. You don't have to specify it. Because in the past, and in the past, I mean the previous versions of the code, you need to establish the feature scaling. However, in classification, that's in regressions. But now in classifications, for some of them may be required to perform the feature scaling because for for the algorithm, it would be difficult to understand what type of scale we are using. While we perform regressions automatically, it's the code understands behind the scenes how to perform the scaling. Does it make sense? And here we need to specify a little bit of feature scaling.
No, that makes sense. Thank you.
Yeah, so that's a very good question. Thanks so much, Enrique. Nevertheless, in the code, I'll guide you through about how to understand that feature scaling, but most of the time would be kind of the factors that we perform. That's another way to say feature scaling, the factoring. Do you remember that we use factors? And based on the factor, we created some classification. That's kind of the equivalence of feature scaling. Okay, like for instance, when we are talking about nearest neighbors, let's imagine that you have a scatter plot. The scatter plot, you have an x1 and x2 axis, which means we have transactions. What the x1 and x2 what it means, it can be, as I told you before, it can be, for instance, revenue and profit, or it can be cost and revenue. What else? What other dimensions do you use on regular basis that can be compared one to each other in the
Models and
scatter?
unit,
I'll come again. Unit and what?
models and units,
There you go.
months and units
Yeah.
sold per month.
Months and units can be x1 and x2. Beautiful. Anyone else? That's the one that we use for regression, right? For regressions over periods. Any other example for x1 and x2?
Users and I'm sorry.
Nothing to be sorry about. Like can be like users and what else? Lisa,
Lifetime value.
come again.
Lifetime value.
Lifetime value, beautiful. Yeah. So you can use any dimension that you may think of. However, if I ask you, please classify them, would be like, oh my God. Let's say that what if, for instance, in the first example, what we would like to classify high-end and lower-end customers, which means the high-end are the ones that actually are purchasing high volume and giving you a huge amount of dollars. And the low end would be those that actually buy less volume and give you, as in consequence, less amount of dollars. But usually you give a discount. And I say usually in order to gain market, right? Sometimes if it's first time customer, you may give certain discount just to perform certain engagement with the customer in order to keep them attracted by your product. You may give certain discount, right? Maybe those are the lower end customers, those ones that actually are trying or attempting to some tryouts of your product and they want to buy it once, and maybe just for the sake of attracting a customer, maybe they buy a small amount of your product, but you actually give a good discount, right? It's the lower end ones. However, those that are actually a very attractive or your product, they say, you know what? I already know your product. I'm gonna buy you a huge amount of units. Maybe you give a certain discount, and it's where actually you may give another category. I don't know, you name it. So you can have your higher end customers and you can have your lower end customers. What is going to happen in a new data point comes across, right? Like for instance, the gray cross that we have here. How would you classify them? Into category one or category two? What side it is closer to?
One.
Category one.
Category one.
One.
Category one. Most probably that one will be categorized as category one. Why? Because based on the distance of the different points, I can infer that that one is closer to category one. But what if it were a little bit more through the edge? Do you think that you can classify it if it were kind of closer to the green one? Most probably not. At least I
When,
wouldn't. Beg your pardon?
but when we have this is type of example with the KNN, and this was a question that I have. Do we set a limit? For example,
Yes.
the last
Yes.
time that we were looking at one example that was very good was the average for entering
Actually,
an university.
yes.
So 5.99999 is not.
Yes, but that first sight is not easy for a human being to identify that threshold. For instance, if it were the 0.1 difference, for me, foresight in a plot would be difficult to identify. However, the algorithm does, as you mentioned. So the algorithm would be able to identify the 0.00000000001 difference, and it would be able to classify it immediately. Does it make sense? That's exactly what we are looking for with these algorithms. No matter how complex, no matter how difficult it is to classify, the algorithm will detect the 0.000, the million zeros that one, and help you to classify it without requiring much effort. Because as you can see here, that's what is called nearest neighbors. Nearest neighbor means which data point is closer, or existing data points are closer to the new data point. So in this case, let's say that's why it's called nearest neighbors. You count how many neighbors are the closest one, and the ones that are closer in a bigger amount are it's where the group that the new data point will belong to. For instance, in this case, the example, the gray cross, right, is white closer to 3 red dots than, or is nearer or nearest to 3 red crosses than the 2 green crosses. Is that crystal clear for everyone in the right-hand side? I mean, it's very, very visible, right? It's very visual, so you can identify that it actually is great, right? Because sometimes I'm colorblind.
Yes,
For me,
that's right.
sometimes it's red, gray, right? Thank you so much, Luis. Yeah, so the gray cross is closer to 3 red crosses rather than the 2 green crosses in the right-hand side. I mean, it's pretty straightforward, right? Very clear and straight. Does anyone disagree with that? Anyone disagrees? Come on, don't be shy. I dare you. I'm just kidding. No, not in this case. But yeah, that's the way that nearest neighbors works. So it identifies the closest data points, or the nearest. That's why it's called nearest neighbors. And the second, the amount of near data points to that one in order to classify it. So, which in this one, I would classify it as red or category 1, or I don't know, you name it, right? At the end of the day, it's closer to that one. So it is easy to classify, at least visually speaking. So in other words, it takes the Euclidean distance. And the Euclidean distance, let me write it here. Actually, I have a pre-prepared drawing. So the Euclidean distance is nothing but the distance between 2 points, right? Which is led by the relationship between x and y, right? Which is nothing but the distance between, and the relationship would be x1 minus x2 divided by y1 minus y2. So don't worry about it. At the end of the day, the algorithm does that calculation on your behalf, but just wanted to let you know that it takes into consideration the distance between 2 points, that's the Euclidean distance. And also it takes into consideration the trend that it has, whether it's decreasing or increasing, but that's the Euclidean distance. So that's the theory behind the scenes that it uses this algorithm, the Euclidean distance between 2 points, and it does the same for all the data points in one shot. And also it creates the Euclidean distance between 1 point and the remaining ones, second data point and the remaining ones, and so on and so forth. So it identifies how far is each and one of the data points among them, and it creates those groups based on that Euclidean distance. So in other words, let's say that you would like to classify this into 2 groups, right? That one is very, very tough. But let's say that you would like to classify this into 2 groups. So maybe I create a curve out of this, and classify it into two groups, right? Which is the group at the bottom and the group at the top. However, to be honest with you, here I identify more than two groups actually. I may say that actually three. What if you want to classify them into three, right? So you have one group here, one group here, and one group here, right? And also, what if you would like to classify them into two more groups, right? Anything and everything is possible with these algorithms, right? What if you only want one group? Okay, guess what? You only take them all, and this is the group that you have. That is for clustering. But what if I have separate groups and I would like to classify them based on the heterogeneous classification that each one of them has? So, in other words, here we have the x-axis. Actually, this is the z-axis. This is the x-axis and the y-axis, right? So maybe now that you have the groups, you would like to classify them. Well, guess what? Let's do that. If I want to classify the first group, okay, I take them all and put them into one classification, right? Now, if I take the group 2 and put them into in the other classification, which is pretty much the same that what I did before, but this time around, the first one was the clustering, which actually the classification applies for the physical chart, and the other one is kind of I'm taking each one of the groups and classify them by my own because I already have the groups, right? So this is kind of a little bit of the theory behind the scenes about what we are doing without requiring to do that effort by your own. The code will do it by its own. Okay. Is there any question so far? Okay, this is a calculation for the Euclidean distance, as I told you before, which is nothing but the sum between the xi, which is x1, x2, x3, x4, x5, that's why it's called with the x, minus y1, y2, x1 minus y1, x2 minus y2, and so on and so forth, and squared. Do you remember how to calculate, I put myself in it, how to calculate the distance? Do you remember that there was an equation to calculate the hypotenusa in a um in a in a
Pythagoras?
triangle? Yeah,
Yes.
the Pythagoras. Do you remember that equation, right? Which
Yes.
is so you have this part, you have you have this particular line, right? This is squared, right? Because that means you have a 90 degrees angle, right? Do you remember the equation to calculate the hypotenusa of this?
A to the square plus b to the square equals c to the square.
Beautiful. As you can see, is the same equation that we have here, which is which is nothing but calculating the distance. When you have an x and y axis, you're calculating the hypotenusa. That's pretty much the exact same example. Just wanted to visualize that, which is nothing but if you have x and y, let me put this example. You have, let's say you have x here, and you have y, right? So pretty much the distance between 2 points is nothing but that. Let me give an example. Let you put here. Oh my God. Let me give between 2 points here, right? Which is the example of x, y, and you're calculating this distance. Would be, as you can see, is nothing but a triangle. Is the exact same equation. You are calculating the distance between two data points, taking into consideration that each one of them has a relationship between x and y. So that's pretty much the analogy behind the scenes. So that's why we use the Euclidean distance, which is the most common. Nevertheless, there's a Manhattan distance, which is the absolute value of the same data points. Rather, with this, what you are saying, you are neutralizing the sign. I mean, you don't want negatives. That's what you are doing, either squared or you are using the absolute value, or in this case, here it's the same as the squared value of the absolute sum of all of them. Go for it, Janet.
So far we have defined or stated the classifications we want, right? I was wondering if R finds out that there is something that does not match with any of the classifications, will it tell us somehow or create a new category?
Yes, actually, yes. If you have only one data point out of those categories would be an outlier, which is an unusual and a unusual value. However, if you have more than the one standard deviation of groups outside of that category would create a new category. In the
Pretty
next
nice.
class, you are welcome. In the next class, we will take a look to clustering. Clustering, you specify how many groups you want. In this case, it would do it by its own. But for clustering, it would happen that, what if I want more than one group, right? So you create the clustering, you specify how many clusters you want, and however, there's a rule out of that, which is going to be an elbow method. The elbow method is nothing but, I'll explain it in clustering. I don't want to confuse you now. Just want you to understand this. So in here, it gives explanation, for instance, between two data points to understand what's the distance, which would be x1 minus x2. I'm sorry, x2 minus x1, apologies. Y2 minus y1 plus all summed up squared, and you have the square root out of that. That's a way that you calculate this distance. Crystal clear for everyone? It's, I mean, kind of basic math, and by say, actually, it's basic algebra. So, is that crystal clear for everyone? I mean, it's not mandatory to understand it kind of step by step the formula. This is not a math class. What I want you to understand, it's what the theory behind the scenes about how it determines the distance between two data points, right? I don't want you to calculate the Euclidean distance manually. This is not secondary school class. This is only to give you an example how it's being calculated and what's the logic behind the scenes. So, I mean, this is the same equation, but using R, right? At the end of the day, is nothing but the sum between xy minus y2 squared and the root. That's it. And this is a further explanation, right? For instance, this is example, but with numbers. We have x1, which is 20, x2, which is 30, y1, which is 12, and y2, which is 8. So you perform 20 minus 30 squared plus 12 minus 8 squared and root squared out of that, and you get 10.77, which is the distance between this point and this point. Crystal clear? Right? Okay, beautiful. That's the Euclidean distance, which is the most common distance that is being used. Nevertheless, this algorithm calculates them all in one shot, which is the beauty about the R algorithm. So the super vector machine is pretty much alike. The only difference is, rather than having groups, it identifies these the extreme values. So it says, you know what? There are two groups. The distance between the extreme data points for each one of the groups is this one. Actually, let me use the pointer. I think it would be better if I use the annotate. For instance, for the red one, this is the limit value. For the green one, this is the limit value. So what it does, it takes the distance between both, establish the limit threshold or the median point between both, creates a vector out of that, and that's why it's called supervector machine. Out of this vector, the new data point that comes across, for instance, a new cross comes across, it's gonna be classified either in this side or in this side, depending upon this threshold. Oh my God, that was horrible. About this threshold, I try to follow my own line, this threshold, and so on and so forth. So that's why it's called supervector machine, because next data point either is gonna fall here or here. What would happen if it goes here, right? You may wonder. Okay, guess what? This is gonna be either classified depending upon the center of the cross. So if it goes 1 millimeter to the right-hand side or to the left-hand side, either way, the algorithm will be able to classify it. Is there any question so far? Okay, so here's the example. Oh, it was pretty much close. Can you see my line? Oh my, I'm an artist. Anyways, aside of data scientist, I'm an artist. Can you see it's very close? Okay, anyways, just kidding. So, as you can see, pretty much as what I said, let me try to clean this up. Oh, internet. Never thought about it. Here we go. Clear. Oh my, there you go. So, as you can see, this the presentation pretty much has that, right? Identifies the distance between the two groups. Based on that distance, create exactly the middle point, which is going to be this, right? Creates a vector exactly in parallel with all of them, and based on that distance, would be able to classify between the two groups. That's the beauty about this algorithm. It does it by its own. You don't have to do anything, but just perform the programming. And once that you perform the programming, you don't have to do it by your own. You can classify in the future any transaction, whether it's fraudulent or not, whether it's accurate or not, whether pass or fail, and so on and so forth. That's why it's called classification, right? Because you can classify any upcoming data points without any problem. However, please bear in mind that this is not exactly, I mean, here I'm trying to say it that is linear, but guess what? This is multidimensional in the sense that it's a plane rather than, actually, this is not a good example. Let me use the lines. For instance, it's a plane in the sense that here is going to create the first classification, right? This is the plane. Imagine that this is nothing but two-dimensional value. So in other words, everything that it's above that plane will be blank classification, which is maybe this. Everything below the plane will be another classification. It's that visual. You need to use your imagination because my drawings are very horrible, but at least I tried. Anyways, just want to explain that it's not exactly linear. You have a 3D projection, and out of that 3D you create a plane, and that is going to help you to divide the data depending upon the different characteristic skill sets and statistical values out of that to classify it. Okay. And guess what? That was all the theory that I was about to show you today. So let's start with the beautiful examples. I think it's better, right? So this time around, we will take a look to those algorithms. So in order to do that, let me open my beautiful R. You already have those algorithms there. As I told you, we will focus into two algorithms. However, we will take a look to one last algorithm just to have it handy. But for classifications, these are the most important. Actually, to be honest with you, the nearest neighbors and support vector machine are the most commonly used. Based on my experience, support vector machine, it's more accurate than nearest neighbors, but it depends upon the example and depends upon the data set or the data sample. I always suggest to start first with logistics regression if you want to classify in binary, and afterward apply nearest neighbors, and last but not least, apply support vector machine. But it's totally up to you. At the end of the day, you're the data scientists, and you'll decide what to use. However, I always suggest you to focus into the confusion matrix, right? So in this case, we will use another data set, actually, which is called, actually, it's the same data set that we used before, which is the social network ads, right? It's the same one that we used before. However, let's take a look to that one. First, let me run the data set and show you why are we choosing between column 3 and 5. Just a moment, please. View data set. There you go. I'm sorry, I'm a little bit cold, so that's the reason why I can hear you can hear me funny. But anyways, so we have the same as yesterday: the user ID, the gender, age, estimated salary, whether those people purchase the product or not. If you remember, it's the same example that we used for the logistics regression. So in this case, however, we will use between column 3 and 5, right? Which is 1, 2, 3, 4, and 5. Only we will use age, estimated salary, and purchase. In contrast with other programming languages, like in Python, if you say between 3 and 5, it does not include the first column. It's just FYI, and for some of you would be a useless information, but just wanted to let you know that depending upon the programming language, it will include or not the first column. I think in C happens the same. I think I think Enrique, you are also you program actually, right? You're also a programmer. Am I correct?
Yes. Yes, I'm
Yeah.
an engineering manager, but yes.
But yeah, but you must be able to, as an engineer manager, most probably you manage more than 2 programming languages, correct?
Yeah, Go, Java, JavaScript, and Python.
Okay, so I think in Java it does include the first value, but in Python it does not include the first value, correct? Into the group.
Probably C++ because Java doesn't include the first value as well.
Okay, same as Python, right? But C++, I think it does include. You're totally right. Yeah. So, however, in R is pretty much like as Java. It includes the first data point that you include into that group. So, in this case, we are saying, you know what? Let's use between column 3 and 5. Again, 1, 2, 3, 4, and 5. It will use age, estimated salary, and purchase, right? So in some other programming languages, it starts from 0. That's another difference. But anyways, here, don't worry. It starts in 1, 2, 3, 4, 5 columns. And based on the threshold that we're establishing, it will use 3, 4, and 5. Crystal clear?
Yeah, but in my table, teacher, in my case, I only have 3. That one. I only have age, etc.
Because you run also the line number 4.
Okay.
Yeah, if you have run only the line number 2 and you view the data set, it will show you the 5 of them. But if you run the line number 5, which is the data set and the squared brackets and between 3 and 5, it actually will limit your data set. And if you run it one more time, you'll have only 3 columns.
Okay, got it. Thank you.
Beautiful. You're welcome. And thank you for asking that question, because at the end of the day, it's important to understand how we can establish the different groups and to identify the meaningful columns to be used as part of our dataset. Now we will create a factoring. In this case, we would like to classify into one group or the other, right? Because we are using a vector. So in this case, we will use data purchased. I'm sorry, this is data set. We will use $, and we will use either purchased. So this is gonna be the binary classification that we will use. Why binary? Because either they purchased or they did not purchase. That's it, right? It's like a flip coin. Either it was head or tails, whether the person came in or went out. It's a binary classification. In this case, if you're selling a product, you have only 2 types of customers: the ones that bought it or the ones that didn't. Is that crystal clear?
Yep.
So in this case, we will create a factor. If you remember, the factor creates nothing but a classification depending upon how many factors you have, right? If you have 2 factors, would be 0 and 1. You have 3 factors, 0, 1, and 2. You have 4 factors, 0, 1, 2, and 3, and so on and so forth. In this case, we will create only 2 factors, which is the difference between, I'm sorry, those that actually purchased and those that actually did not. Purchased, how many levels we will have? How many levels? Two levels. Beautiful. We will have only 2 levels, which is a vector out of 0 and 1, where actually 0 are the ones that did not purchase the product, and 1 are the ones that actually purchased the product. That's the classification that we are doing here. However, you may wonder, but Fer, we already have that data set in here. But guess what? The algorithm doesn't know what this 0 or 1 means. So that's exactly what we are doing here. We are saying, you don't know what? You know what? This particular category between 0 and 1, we are saying it are two factors. So that 0 and 1 are not numbers, are factors. So each time you find a 0 means something, and each time you find a 1 means something, which means you'll create two groups. All the data that comes with zeros will be in one group, and those that come with ones, actually, let me sort it out. Those that come with ones, it's another group. Crystal clear? What we're doing with the factors here, we're creating two groups out of the dataset. The ones that purchased and the one that did not. Crystal clear? That's exactly what we are doing here. Questions?
No.
Okay. So now we will invoke another library. I'm sorry, we will invoke our library that in this case is the exact same library that we have used so far, which is CA-Tools. CA-Tools is nothing but the library that will help us with linear regression and some classifications that are the most basic, and we will use the same one. We will use the set seed as we have done before, which means what? A volunteer. What does, I mean, I have asked this like 100 times, but I really want to, I love to hear it. Who can tell me what set seed stands for? What is that being used for?
Random. Randomized, right? Numbers.
There you go. So you take random numbers. Here we're saying you'll take random numbers. Here we are saying consecutive numbers. However, it can be any numbers within. Just you're saying out of arrange your data set between 0 and, I'm sorry, between 1 and X number, sort them, and take random values out of that. It's what we are saying here. I know that I repeat this like 100 times, but that's the way that you're going to be repeating it. So in here, we will create the split, if you remember. So in the split, we will create a variable called split, and we will use sample.split, sample split, and within we will say, you know what? Let's take into consideration the data set, which is the universe of data that we have, but specifically, we will take into consideration whether they purchased or not, and we will split the ratio. Actually, there's an error in the code that you have. There's an error in the code that you have. What's the error? I did it in purpose though.
That 0.75?
In what's wrong with that?
I
More
think
than
we have used 0.4 as 40%, no?
At least or at most?
Uh-huh.
And that's your question.
Oh, I'm
most.
sorry.
No worries.
at most.
At most.
There you go. Exactly. So dot 75. What are we doing with the dot 75?
We are
Overfitting.
taking more data.
Overfitting. Exactly. We're taking more data and we're overfitting. Overfitting means we are forcing the model to behave in the fashion that we want. And we don't want that. We will take only 0.4 or 0.40%. Exactly. I did it in purpose that code has an error because I wanted you to identify it. So very good point. What is remaining? We need to train that data set, right? Training underscore set. Oh my God, training underscore. What is the underscore set? There you go. An equal sign equal to subset because we will create a smaller amount of data set out of the entire world. And in this case, we will use the data set that we have already. And out of the data set, we will perform a split. And as per being the first sample, out of that 40%, what is going to be? True or false?
True.
True. Beautiful. Exactly. Because what we're saying, we are going to take this 40% and it's going to be stored in the training set. If we say false, what would happen?
It will take the 60%, wasn't it?
Exactly. And what would be? And a what? What would be the problem there?
That's an overfitting.
Overfitting. Exactly. Exactly. Now, are you catching every single point? What are we doing? Everything? So you are doing great, actually. I'm very proud of all of you. Test set equal to subset. It's another subset, which is gonna be data set. Same thing, split. And in this case, what we would like to take? The remaining data, right? So in order to do so, what we need to specify in the test set?
False.
False, because we are taking the remaining values out of the 40%, which are going to be 0.6%, right? Or 60% of the entire data set. What is going to be taken here? Okay, beautiful. Now let's run them all and see, okay, we don't get any error. And actually, all of them were stored in the right-hand side. So we have a data set, we have a sample, a split, test set, and training set. Actually, I have more than that. Why do we have them all? I think it's stored from other data set. Let me redo that because I don't want to pollute my data. Let's create the factor. Let's create the factor. Let's run the CA tools, sample. Let me take the split 40%, create the test set and the training set. Here we go. We must have only 4 variables that are the ones that come as part of the data set. The first one is the main data set. Second, the transformation or the extrapolation of that data set. Afterward, the split, training set, and test set is what we have in the right-hand side, correct? And as you can see, we have 400 values. It's a huge amount, right? And actually, we can have more. Honestly, I'm lazy. I don't want to do it manually. That's why I learned how to code. And maybe you have other reasons, but for me, is that I'm lazy. I don't want to work more than I supposed to. Anyways, so that's another conversation with my psychiatrist. So now we need to perform the feature scaling. In the classification models, we need to do the feature scaling because here we need to specify what are the thresholds for our canvas. Else, it may give us an error because it doesn't know how to plot it. So in this case, we will do the feature scaling. And in order to do the feature scaling, it will say, you know what? Here is feature scaling. So here we are going to say, you know what? Take the training set, all the values, minus the last one, which is going to be, okay, what is the squared thing? There you go. Here we go. The training says we take squared brackets and we will say, you know what? Take all the entire data set, but do not include the last one. How we do say so? We say -3. If you remember how many columns we had? 1, 2, 3. So in other words, for the feature scaling, we will use the age and the estimated salary. That's why we are saying take all of them, but the third one, the -3 means take everything but the last one. 1, 2, 3. But if we go the other way around, it will be -3, -2, -1. Crystal clear? If we go from left to right, would be 1, 2, 3. But if we go from right to left, it would be -3, -2, -1. That's why we say here, this is another nomenclature to say, please take the last one. Crystal clear? Because we only have 3 columns. If we had 10 columns, what would be the number in here if we want to get rid of the last column?
-10.
-10. Beautiful. -9 if you want to get rid of the previous last. So, and so on and so forth. So you can go either left to right or right to left. Here is to go from right to left. So in here we are saying, you know what? Include them all, but the last column. And you'll perform a transformation. What would be the transformation? Scale, which means adapt the data set to the canvas available. That's the scale, what it means for. Go ahead, Monica.
And I know you can use head and visualize all of the titles of the columns, but if you have a super large data set and you don't necessarily want to do a manual error, can you call it by name? instead of by position?
Of course. You can do it either by name, by positional value, or by alias. You can assign an alias, and you can use alias, you can use positional value, or you can use the name of the column.
Okay. So you would call it, let's say, in this example, you would just put it in parentheses, or how? Yeah.
Yeah, you would use the square brackets and the double quotes to say, you know what, the name of the column, you can do that as well.
Thanks.
You are welcome. Is there any other question so far? That's a beautiful question, though. This is the first time that is being asked. I think you should get an extra point because of that. But I'll think about it.
My team agrees.
A big one?
My team agrees, yes.
I love the democracy, but let's think about it. Anyways, so what we're doing here, we're saying, you know what? Take the entire dataset and create the feature scaling. What if we take a look to the feature scaling? Why? That way you'll understand what we're talking about. And if you remember, it will have nothing but if you have what it's gonna do here, I didn't explain it before, just like that. But imagine that you have, actually, this is not example, but imagine that you have this. You have a cardinal situation here. And instead of saying, you know what, put here millions of dollars, here millions of dollars. Let me change the color. That one is annoying. Let me change the color. Let's say here you have the cross here, and you have the cross here. And let's say, like, instead of saying, you know what, $1 million here, instead of $1 million, would be perhaps a scale between -1 and +1. Actually, this one would be between -2 and 2, actually, based on the numbers, top of mind. So let's say that here, instead of using -$2 million and +$2 million, instead you say, you know what? I don't want to overcomplicate things. I want to say, guess what? Instead of over -$2 million, it would be -2, which is the scale. -2 and +2. So each and one of the values, like if it were rather than 500,000 minus 500,000 would be -0.5, correct? It would be -0.5, something like this. And 1.8, which would be something like this. Oh my God. This would be the analogy out of that for the first value, right? So this would be the first data point and so on and so forth. That's what we do with the feature scaling. Instead of using $1 million, we translate it into a canvas and we assign centimeters or inches for that value. For let's say that $1 million instead of $1 million is an inch, and $2 million would be 2 inches, and so on and so forth. Same for the X and Y axis. Someone had a question.
No, it was me, but you explained how it works with the scaling, so it's good. It's good.
Because I read minds. That's the reason why.
Yeah.
I wish I could. Anyways, I'm glad to hear that I answered that question. So guess what? We have already performed a feature scaling for the training set, but we need to perform another feature scaling. Which one?
For the test set.
For the test set. Else, how are we planning to plot it, right? So we need to perform also feature scaling for the test set. So let's do the same. So it's going to be exactly the same. We will take all the columns, but the last one, but this time around will be for the test set, which is nothing but for the remaining 60% of the data that we would like to analyze. Straightforward, crystal clear, correct? So guess what? You have more than 60% of the work done. You have already trained your data. You have taken your sample. You have trained your data. You have tested the remaining data, and you have performed the feature scaling. The only thing that is remaining is to adapt those things to the subclassifier, which is the support vector machine. Go ahead, Alonso.
What would happen if you have another column in the database, which is maybe alphabetical, for example, a customer name, do you need to remove that as well before you do the feature scaling, or what would happen to that?
Yes, yes, actually, yes, because the name of the person is not important so far, not now. Because first we need to understand the transactions. We need to understand how sparse those are. We need to understand the statistical factors out of the data. And afterward, once that we have performed those analyses, of course we can classify them. We can identify the person who is earning the most, who is earning the less, or something like that. However, for statistical purposes, we need to take into account the entire universe of data. Does it make sense? Because the person name, it's unique. It doesn't work for statistical factors. It doesn't work for statistical values. Does it make sense?
Yeah, thank you.
You are welcome, because with statistics, what you would like to do, generalize, understand patterns, understand everything as a whole. Unfortunately, individuals are not important here. We would like to understand trends, patterns, factors. We would like to understand how can we classify, how can we understand what is the direction for that trend, how to predict something. Because individuals in here will be important only for specific analysis, but here we are performing overall analysis. Of course, we can take into consideration an individual in the future because that would be kind of a main target, right? Once that we have identified the groups, that once that we have identified what are the thresholds, maybe that person belongs to that high end group, and maybe we would like to offer a Tesla. Maybe if it were a lower end, we can offer a Honda City. Oh my God, why are you talking about my car? You have less points because of that. But anyways, if you are talking about lower end, maybe you're offering a Honda City. Maybe if you are talking about a middle end people for income, you may offer a BMW, right? Or maybe it's high end as well. It depends upon what the factors there, because maybe someone is not likely to choose an electrical car, so then you have the binary classification again, right? High end, which actually would like to have a electrical car, or maybe those that actually would like to have a hybrid, or maybe those that would like to have a gasoline car. Does it make sense where we aiming with this? But that's once that you understood, this is for understanding the data. Once that you understand the data, you can perform any actions that you may think of at group level or individuals level. I'm too intense, right? I mean, I sound like if I were angry. No, no, I'm excited more than angry, so don't worry about it. I'm sorry. Don't want to freak you out. So anyways, so in this case, hopefully I didn't freak you out. And so here we will use another library, which is, I think it's the let me remind, it's I think 1071, I think. E71, there you go. Oh, thank you, little code, for helping me with that. That's a great advantage of this. If you remember only the first things it will give you suggestions based on historical values that you have used. So in this case, we will create another object because we need to classify our data. So we will create an object called classifier, right? This is the name of the object that we will create. Remember, an object can contain list, can contain integers, can contain decimal values, can contain a group of values, if you remember that. An object can contain whatever you want. In this case, we will use a new method, which is called SVM, which stands for any volunteer? Yes, what else?
Matrix? No.
Very close, very close. Remember Terminator. Support vector what?
Machine?
There you go, beautiful. Those are the clues that I use in order to remember things. Like for instance,
Very good.
yeah, I love those analogies, so that's the reason why I tend to share those with you. When I forget about something, I remember support vector. Oh, Terminator, machine. There you go. Maybe I'm too apocalyptical guy, but that's the way I remember things. So I mean, you can use something softer, something my kind of Disney thing, but for me, this one works. Anyways, so forget about what I said. Okay, now we will use a formula. Do you remember what we used in formula? Do you remember? We established which one is the pivot. Do you remember the pivoting, which is the dependent and the dependent variable? In this case, which one is the dependent variable?
Purchased.
Purchase, beautiful, purchased, amazing. You are doing a great job. I'm proud of all of you. And we use the curved dash. If I could remember how to do it, let me change to English because I have it in Spanish. You know what? I keep it in English. I think would be way better. Okay, the curved dash. And what do we use in order to include the more, the remaining values outside the purchase? Do you remember what was the wild card?
Yeah, like
Dot
a
and
dot
comma.
and a
A dot. Beautiful. A dot. And the separator, what would be? Because I tend to forget the freaking separators. Would be what?
Comma.
A comma. Beautiful. Now we are saying we will include other factors. In this case, what's the data? If we are training the model, what data are we using?
Training.
The training set. Beautiful. Exactly. So we will use training set, and we need to use what to separate among the different factors that we are using or features, a comma, right? Because last time I forgot, that's why I'm trying to punish myself. Anyways, so in this case, we will specify that the type, it's important to bear in mind. And in this case, we will use a classification. A classification. Last time, do you remember what we used? It was logistic regression, if you remember. So in this case, it was type. This time is classification, and we will say we will use a kernel. Kernel. Kernel is nothing but the type of classification that we will use. Go ahead, Carlos.
Thank you. Why are we using the training set and not the training set without the third column, since it was the one that we scaled?
Because here that's a very good point. Indeed, we are using at the end of the day, because this one is not the real data, it's scale. So we need to train the model based on the real data. Here we are performing the feature scaling only for plotting purposes.
Okay.
But for training the model, we need to use the training set, which is nothing but real values out of the data. But that's an amazing question. Thank you for that. Wow, this is the group that actually have made the most interesting questions ever. So congratulations. But thank you so much. Yes, because you need to take the real data. Actually, I think, to be honest with you, if you take the scaled one, would be exactly the same because at the end of the day, it's using the same patterns to take the different factors out of the data. So I think it would work as well. But that's a very good question. Go ahead, Claudia.
I read that sometimes you need to use feature scaling in order to put all your features in the same scale, because if not, you can produce bias.
Exactly. Because that's a very good point. The feature scaling, yeah, but at the end of the day, you use the feature scaling for the entire data or you use the entire data. The feature scaling, but you create bias when you only scale one piece of data and the other one you do not. Does it clarify your concern?
Because, for example, when you have a salary, you have 1,000 of
Exactly.
amount.
Exactly.
With the age, you only have 2 digits. So the coefficient could be calculated
by 10.
Yes.
Or by 100, depending upon. Yes, you're totally right. As long as you apply, if you apply feature scaling, you must apply to the entire data set. Else, if you cannot apply to the entire data set, you need to select when to use it, the feature scaling. Like for instance, in this case, we are not using it because we are training our model. In here, we are saying, you know what? Learn from the entire data set, use the dependent variable is purchase. So in other words, please bear in mind how purchase changes based on the other data. It's what we are saying here. Please focus on purchased and the other data is changing. The other data is changing. And now identify how is purchasing changing based on that data. But we are taking into consideration the way the data is. But if we wanted to train it, we will need to perform feature scaling also. Actually, no. For the purchase, no, because at the end of the day, it's two states. So yeah, we can also use that to avoid bias, but we need to apply the feature scaling for the entire data set when we are talking about amounts. Does it clarify and actually your comment's pretty accurate. Thank you so much. Okay, now let's train our model. So as you can see, it created a new object, which it says, you know what? It's a classifier, which is an SVM formula, support vector machine formula. And it is including the size is 19 kilobytes, and it is using a list of 31 objects. You can take a look by using the view and so on and so forth, but honestly, it doesn't make that much sense because it has scaled values. So now we need to create a new object, which is the y_pred, y_pred, which is nothing but the objects that will store the prediction that we will discussing about. So we will use the method called predict, and within we will use what object? What are we gonna use to perform the prediction? The object
Classifier?
the classifier, beautiful, because the classifier contains the rules that we will apply to the entire data set to give the efforts and the results out of that. Crystal clear? However, we will use a new data, right? The new data is nothing but this time around we will use the feature scaled. Why? Because we need to adapt it to the canvas. We need to adapt it to the area. We need to normalize it. So in this case, we will use the test set, and we will use only the columns that we require, which is all of them minus the third one. In this case, we'll use the feature scaled. Okay, here we go. And you may wonder, why are we using this feature scaling in this case? Because here we are gonna plot the predictions. So that's why we perform the feature scaling, to adapt it to the canvas that we have available to plot it. So here we are normalizing the data to speak apples to apples. That's what we are doing here. Now, guess what? We have performed the predictions. But here we will include another object, which is called the confusion matrix. The confusion matrix, I already explained it in last class, but either way here we're going to elaborate the most. So can anybody remind me what the confusion matrix it's all about?
It talks about the true, false, and the false, true.
Beautiful.
False positive, sorry.
Actually, you explained it well in very simple words. The true values and the false predictions, or the true predictions and the false predictions, right? In other words, something that was expected to be true, whether it's true. Something that was expected to be false and was false. The other way around, something that was expected to be true and was false. That's an error. And something that was expected to be false and is true, another error. So I'll show you how to calculate the level of accuracy of your prediction. So in this case, we will use the object y_pred, and let's take a look to that. So here we go. It created a new object, which is confusion matrix. And as you can see, it creates some objects that are out of that. So let's take a look to the confusion matrix, what it's all about. And let's take a look. So in this case, let's take a look. Something that was expected, something that is false and was expected to be false, 143, which is an accurate prediction, correct? Now the other prediction that was supposed to be true, something that was expected to be true and actually was true with the prediction, 74. Crystal clear? So let's sum up those ones, which is gonna be 217, correct? 217, top of mind. 217 because it's 143, 43, and 74. Correct? Actually, if you are unclear, you can use it here. 143 plus 74. Oh my God. Plus 74. 217. Here we go. That's the total. And however, let's identify the errors. 12 plus 11. 12 plus 11, well, straightforward, 23, right? So the accuracy of the model will be the comparison between the errors and the total values, which would be 100%, which would be in this case would be 217 plus 23, right? That would be the universe, entire universe, plus 23. So the percentage of error would be 23 divided by this, correct? So in other words, we have 9.5% of error, which means the accuracy would be 100% minus 9.5 means our model has an accuracy of 90.5%, which means it's very close to perfection. Is that crystal clear? Crystal clear for everyone?
Yeah. So it's like 90% effective, right?
Exactly. That means the efficacy or perfection of our model is 91% pretty much of our predictions. Crystal clear? Okay. Now, what if we take a look about how it looks like? Do you find it useful? Okay. So in order to do that, let's take a look to the universe of data, how it looked like. We will use, actually, I'll copy everything. I don't write it. I don't want to write it down. So in here, let's plot the data. So far, we will plot only the data. So let's take a look to the data. So in here, at the bottom, as you can see, this is the feature scaling. Instead of putting 20 years, 70 years, the minimum amount would be -3, and the maximum years would be 3. That's kind of to give you the idea about how feature scaling works. Go ahead, Maria.
Fernando, can you send that code in the chat, please?
It is available in the practice, wasn't it?
Yeah, I believe, but you can send it. Sorry.
No, that's fine. Do you mean for the plot or the entire data set?
No, the graph, only the plot.
There you go. You have it now. For the first part of the plot is here. So what we are doing, we are plotting the existing data. In other words, however, we are doing feature scaling. In this case, what means, let's sort out the age just to show you what feature scaling means, which means the 18 is nothing but the -3, and the 60 would be the 3. And everything in the middle would be the scaling of all the data points that may match depending upon the positional value of each one of them. Crystal clear? It's clear, right?
Yeah.
Same for, go ahead.
Yeah, sorry, I got a question.
No, nothing to be sorry about.
I understood on the age, the -3 will be your youngest age and the 3 will be your oldest age, which is 60.
Exactly.
And same applies with salary, right? Like -2
Exactly.
is your... Okay. Yeah, that's fine.
Yeah, exactly. For instance, in the salary, let me plot it in here. The 15 at the 150, 100 would be the minimum wage, the minimum wages here, and the maximum wages would be 150,000 would be the +3, right?
Okay.
Would be the equivalent, and everything in the middle will fall into the different categories. You may wonder, why do we do this? To create scale that can be plotted into an area in front of you. That's pretty much the on purpose, to provide the same scale for each one of them to avoid bias. Who was the smart person who actually said so, aside me? Was you, Janet, or who said that the feature scaling is used for that, to avoid bias? Who was it? Monse? I'm sorry.
Claudia.
Who said so?
I think it was Claudia.
Claudia.
Claudia. Gloria, thank you so
It, de-
much.
it depends. Are you gonna give an extra point?
No, just because you asked, I would say no.
Okay.
I was aiming to, but now that you were so interested, I think I avoided to give extra points. Just to give recognition. Congratulations, Gloria. Great job. Okay, because of this guy, you lost the point. Anyways, so let's take a look now to the code again. Apologies. If someone feels offended, please let me know. And afterward, what is missing here? So is the data classified so far? I mean, can we understand what's going on here? Guess what? Let's include the classification into the plot. So because we have already classified the data, and by classifying the data means let's include the two groups that we have, those that actually purchased the product, those that did not purchase the product, and also the mistakes that we made in the prediction, or the those that actually we thought that were about to buy the product, and those that actually did not buy the product, and those that we predicted that would not buy the product and actually bought the product. So it's taking a while because my computer requires some memory. But here what we are doing, here we're including the contour. The contour is nothing but the thresholds and the limits. Here we are saying, you know what, for based on X1 and X2, based on the matrix that we created, based on the predictions, you'll create a threshold. The threshold will be nothing but a picture. You know what? For avoiding this, let me bring the memory, the image that I already had, because I don't want you to, actually, this is the kernel, apologies, this is not the one. Oh, I called it kernel. Why did I call it kernel? This is not the Kernel-SVM. Oh, I named it like that. But actually, this is the SVM only. SVM only. So ignore that piece. But at the end of the day, it's the same chart. But you know what? Let me put it into here. What it's gonna do, as soon as it finishes processing, this time around, I want to avoid the shame of not showing the chart. So in this case, let me use the zoom. You know what? It's gonna take a while as well. So what we are doing here, if I zoom up a little bit, zoom, zoom, zoom. Okay, here, what we are saying, I agree with that, baby. So what we are doing here, so the same chart, which are the transactions, the blue area means those that actually were expected to purchase our product. Those in the red area, were those the one that were predicted not to purchase of product, right? So what it did, it created, based on the test set, created this threshold. Afterward, any upcoming person would be classified based on that threshold. Let's say that it's a person that has an income of, let me check, what is the data set? Oh, maybe I removed it, or what the heck? Okay, let me go to the other one. Here we go. Here in the data set, we said, you know what? Someone whom actually it's earning, let me go all the way through pretty much the threshold. The threshold pretty much is around here. Around here, it's, oh, well, actually it's too biased. Like for instance, here, between 31 and 49 years old with an income of, oh, there you go. And then suddenly it appears the freaking thing. It takes a while. But anyways, so let's imagine that a new person who actually is around 43 years old and is earning $91,000. Most probably that person will be predicted to actually purchase the product, right? Can you see that? However, someone who actually it's around 27 years old and earning around $80,000, I may predict that that person won't buy the product. Guess what? We have some errors here. For instance, this person whom actually is earning around, let me take a look to the threshold, if it wanted to load, but it would be a person kind of between the 20s and actually earning a huge amount of money. That's what this blue point is telling us all about. Same for these three blue points. However, why did it classify it this way? Because at the end of the day, we can see that there's a huge bias here. That's why these 3 data points and 4 data points are outliers, because those on this go out of the norm. Those are people that are very young, that are earning a huge amount of money, that go out of the norm. That's the reason why these blue data points can be either an error, a manual error, someone that actually included an extra zero for that person, or actually young people that is earning a huge amount of money and they are purchasing or they are buying a high-end product. Does it make sense? That actually it happens in the real world, right? Go ahead, Alfonso.
Yeah, I just wanted to ask because my graph looks a little bit different in terms of the colors. Basically, it's split in half with the diagonal line. And the left side is red and the right side is blue. I don't know if I'm the only one.
Me too.
I was gonna ask the same. Yes.
Let me check. Maybe I took.
There are different codes in the files. So
Okay, let
if you
me.
go lower, the something similar to this one, it's there as well.
Let me check. So, did you happen to open? Okay, the nearest neighbors one, the one that says KNN, because there are 3 codes there.
Oh,
The
yeah, no,
K.
I was
There's the.
using the SVM.
Yeah, please. That's why I mentioned that. The first one is KNN, which is nearest neighbors. The second one is support vector machine, and the last but not least would be Kernel-SVM. SVM.
I get confused because the code that we are making now is from the other version of SVM.
No, this must be KNN. The one that says KNN.
But
And
why is the graph
actually,
name as SVM then?
it was an error here. When I copy and paste
Okay.
the code, it was my error. But yeah, actually the code here I can say here. This is a support vector machine. Oh, you're right. Let me check. Just a moment, please.
Yeah, it was mixed right there when
Yeah,
we
you know
entered the
what?
library.
Yeah, this is the SVM. However, but the colors are different, right? But the chart is different. Is the same, or which one you run the KNN? You're
The
totally
data
right.
points are the same. It's just the colors of the
The
chart.
colors are different, right? So what
Yeah.
colors do you have?
Same red and blue, but with like a diagonal line split.
Oh, the diagonal line. Okay, you know what? Yeah, that's a support vector. That's the KNN. So you are right. So here I ran the support vector machine, but let me run the KNN. Let me do that. Let's go for the KNN. But yeah, I don't want to confuse you. That may cause confusion. It was let me take a look to that one. Okay, so it will be pretty much the same for KNN. So I'll copy everything, just make some changes in here. So we will use the exact same, we will use the exact same data set, the same columns, right? We will use the exact same logic for the levels. The only thing that we will change, just let me, we will change here the model, the classifier. Actually, it's a very good practice. So instead of SVM, let's change it to KNN. And the KNN, let's use, in this case, we will use the training in here. Let's use here the training. It changes. Again, we will use the same data set, which is the neural networks. We will use the same columns. We will create the same factors because at the end of the day, it's the same thing, right? We will identify who purchased and who doesn't. We will use the same split, which is actually, in this one, let's change it to 30% to show you that actually it works as well because it learns from the data. So let's do that. And you know what? Let me copy everything. This is the other algorithm. And let me name it here KNN. So the KNN in here, this time around, we will use a different library. The library, no, actually it's the same library. No, the library, it's class, if I am not mistaken. So please, did you install the libraries that I asked you in the message? One of them is class. Class is being used for KNN. Go ahead, Carlos.
I'm confused because in the code in the whiteboard we were using SVM, but in KNN we are using KNN in the widespread. So why are we running the KNN chart in the SVM code?
The model's one thing,
Mm-hmm.
but the chart, you can change whatever you want. So I think the confusion is the name of the chart. So
Okay.
in here, let's fix the name of the chart. So in this case, let me show you here. Actually, we're gonna fix that confusion.
Okay.
So in here, for instance, this is the chart. Let me change the name. Here is gonna be KNN. Okay, so in here, let me fix that situation. Now we will run KNN. So we will use the exact training set and everything. The only thing that we will change is the classifier. In the classifier, we will use here, instead of formula, we will use train. And within train, in this case, we will use the training set. Here, we're gonna use the scaled, the feature scaled data set. Crystal clear? The entry instead of data, this one will be test. And within test, we will use the exact same amount, but I'm sorry, the exact same threshold, but for the test set instead of the training set. So in this case will be for the test, of course, will be test set, but scaled, right? And afterward, we will use another object, which is called CL, which is gonna be also must be the training set as well. Here we go, the training set. And also in here, we need to include the K. The K means how many vectors, how many classifications we would like to include. The default is 6. The default is 6. However, you can play with that. And the probability in here, we will use a factor which is called prob, which is probability equal to, it will be to true. We would like to use the probability that something is true. So this is the only difference. In the other model, if you remember, you may have it handy. In this case, instead of using, we are using a different library, which is class, right? And instead of using SVM, support vector machine, SVM, we are using KNN. Now let's run them all. In order to create an object, plus different lengths. Let me check. Let me rerun them all. Let me create this. First, the training set and the test set. Here we go. Afterward, the feature scaling. For the test set feature scaling, let's invoke the library class and let's run our classifier. And in this case, it is like this. Let me check what's going on here. Oh, I'm sorry. Here we need to include the comma within because we would like to include all the rows and only all the columns but the last one. So here there's a little mistake because we need to include all the rows because I only included the first row with that statement. So here let me include all the rows. And which one is missing? It's minor comma. Oh, sorry. In this one, in the training set, we are taking the 3 columns. I'm sorry, the training set, we are taking only the last column, which is the number 3. Here we go. Now with the classifier, let me put it into the chat. This is the change that we made to the model. Where's my mouse? Here we go. Find new. I have an error. Update the function. Carlos is working fine. Are we taking a break? You know what? Beautiful, Carlos. Yeah, the one that you showed is the SVM. Now let's take a look to the KNN. So this is the classifier for nearest neighbors, which is a slightly different, right? In this case, we are using a different model. Yes, after we finish with this model, we will take a break, if you agree. So as you can see, pretty much the preparation, the training, and everything is pretty much alike. The only difference is that we will use a different classifier. Rather than using SVN, which is support vector machine, this time around we will use nearest neighbors. Which nearest neighbors? Let's take a look how it works. Now, in this case, let me take a look to the prediction. The prediction object, this one is the widespread. Actually, you know what? Instead of classifier here, it will be the widespread. This is directly, unfortunately, with KNN, the model and the dependent variable and the prediction is pretty much the same. So let me declare it here, widespread. And here we go. In this case, we can create also the confusion matrix, and this one would be using the widespread, and we can create the confusion matrix. And let's take a look to the confusion matrix to see what's the accuracy. As you can see, we have 169 plus 83, which would be 240, which would be 252. Do you agree? 252 correct, while we have only 28 mistakes, right? Crystal clear about the confusion matrix? Does anyone has any question? Okay, so now we will use the exact same library. So in this case, let's take a look to the object. But in this case, we need to change the plot actually, because we need to use the number, the K. Let me take the other chart to show you how it looks like. Take the other chart. Because here we need to use also the number. Here, the difference is that we are using a K here. The K here means how many classifications groups we are using as part of that. So now let's create the chart, and this time around it must show a linear separation. Usually it must show kind of an L or something like that that must classify the data. Carlos, can you please show us the chart? Did it show it differently, right? Your chart.
I think it was Alfonso.
Alfonso? Alfonso, sorry. Alfonso, can you please share your screen to show the chart that you got? It must have been the same data, but the classification must have been kind of an L. Am I right? Can you please?
It's loading.
It's loading for you as well? Okay.
Yeah.
Meanwhile, okay.
I think I have it.
Can you please share it, please?
Yeah.
While mine is loading.
Is this?
It's coming along. There you go. Yeah, well, actually more than an L is a diagonal. As you can see here in this chart, in a difference of support vector machine, this one is a linear classification, right? So we can see, why can we identify that it's a linear, it's not a linear classification, I'm sorry. It's a classification that actually use a plane rather than a line. So it's divided into groups, but imagine that this is in 3D. It's not 2D as we can see it here. So this is helping us to identify in a 2D what would be a 3D classification, but in a very simple way. Those, if you can see, the line divides for the left-hand side, it is letting us know, you know what? Left-hand side means those that were predicted not to purchase the product is the red side, and the blue side are the ones that actually were told that were predicted that and also trained that were expected to buy your product. For instance, in the left-hand side, how many blue dots we can see? Those are around 10 blue dots, which means predictions that we expected people that weren't about to buy the product, but guess what? Those actually bought it. And in the right-hand side, the blue side means all of them were expected to buy your product, and the red ones, on despite they have the age, and on despite they have the income, they actually didn't buy our product. So before we take in the break, is there any question? Do you see the difference between the two models? This one, as you can see, there's a linear division, right, into both. However, the other one, which is the nearest neighbors, is more accurate because it took a curve, taking into consideration those three dots in the blue line that are pretty close to the edge. Can you see them? Can you see those three dots that are very close to the edge? this algorithm doesn't detect it because at the end of the day, the plane only takes a linear separation. However, when we use a vector or a support vector machine, adapts and includes those three objects or three red dots that are in the edge, which help us to increase the accuracy. That's the reason why support vector machine is more accurate than nearest neighbors because it's not linear. Does it make
So
sense?
basically, both models have the same purpose. The difference is the accuracy. Is that it?
Or yes. However, in some cases, support vector machine may work better than nearest neighbors and the other way around.
Okay.
So my suggestion is always to apply them all.
To try both.
Apply them both. Yes. And the ones that give you the closest accuracy is the one that you should take into consideration. That's why I teach you both. Because you need to compare them. And also the last one, the last but not least, which is going to be the Kernel-SVM, uses the kernel, which is something that I'm going to explain after the break, which tentatively is more accurate than these two, but when the data is too sparse. But when the data is homogeneous, both KNN and support vector machine may be more accurate than Kernel-SVM. So the suggestion is to use the three of them when you have this sparse data to classify them, and depending upon the ones that is giving you more accuracy is the one that you must use for your predictions. Okay, is there any questions so far before we go to the break? Let's take 10 minutes break, please, and let's return back by 27 past 8. So whomever has a question, you may stay. Else, please go to any needs that you may have. Thank you so much. See you in 10 minutes. Against the others. That's where it finds the bias or the distance among all the data points. Does it clarify a little bit what I'm trying to say with these objects? Does anyone have any question?
Not at the moment. Thank you, Fernando. Appreciate the explanation.
It's my pleasure. Hopefully, sometimes when I explain more, I tend to confuse more people, but hopefully it clarified a little bit about what we are doing here. Okay, I think we, at what time I said that we should return back? Apologies.
27.
27. So that means that 3 minutes passed, right? Those that did not take a break, apologize. But now let's continue with last but not least, model. Before we continue, is there any other questions so far? I know that this one's may be a little bit trickier, but at the end of the day, what's the important thing about this is that the process is the same. We take a sample. In this case, well, let me open the objects. In this case, we are taking the data set. Out of the data set, we are taking the dependent and independent variables. And we are ignoring those variables that are not important for the analysis, correct? That's why you need to bear in mind that not all the information that comes in your data set, it's important. You need to understand which ones are the most important, and that's the key for each analysis. Sometimes you may want to try it with some variables, and if those do not work, just for the sake of a scientist, my approach, you may want to try others. For me, it has been a surprise that sometimes I think that I'm sure which ones are the dependent and independent variables, and suddenly the model is not accurate. So I need to analyze the data, and maybe there's another column. Let's say, let me give you an example. If I go to the dataset, so far I used the age, estimated salary, and purchase. We have also the gender, if you remember. Sometimes if the model is not accurate, try to use another column. Try to switch, for instance, between age and gender instead to see whether the accuracy increases. Maybe switch estimated salary, of course, is important because that's a pragmatical value. what I'm talking about are the categories. In this case, we're using age. If you want to use gender instead, also can be important for specific models. Like for instance, if you are selling a particular product that you may think of that would be focused to a particular gender, of course, you must need to include it into your model. So those are the things that you need to bear in mind. At the end of the day here, I created some factors. The factors is nothing to identify which one the successful test and which one was the unsuccessful test for saying something. There's no right or wrong. At the end of the day are facts. So either they purchased or they didn't. That's a fact. There's nothing wrong with that. There's no error, there's no mistake. It's the real world. Afterward, we take the sample, we train the model, we test the model. I'm sorry. First, we take the sample, which is the training and the test set, and afterward, here we train our model, where we apply the KNN, or we apply the SVM, or we apply any other model. In the last one, I'll show you a mix of both models. So for the sake of the time that we have 27 minutes left, I'll bring the example that I already have published for you. Actually, random forest, this is another model that I did not share with you. Why? Because this is less accurate, to be honest with you, and I barely used it. But this one, instead of creating a three-dimensional like this one, it creates like an L and simply selects all the values. But it's not part of the class, so don't worry about it. But I wanted to show, but I'll share this code with you just to have it handy in case you want to try it and compare it among others. I'm sorry, I'm a little bit sick. But the other model that, for instance, we took a look to the support vector machine, right? So the Kernel-SVM, actually, this is the Kernel-SVM, the one that we took a look to. And the SVM alone combines both, combines the KNN and combines the support vector machine all together. Why? Because the KNN, at the end of the day, I told you that is less accurate, right? I told you that KNN technically performs a classification out of the data, but the support vector machine performs a perfection of that particular data set. So that's why I separated into both. First, we took a look to the KNN alone and the SVM alone. But this one, if we mix both together, let's see how the accuracy increases. Do you agree with that? Is that crystal clear? If you remember, we saw first KNN and afterward, first we took a look to SVM, afterward to KNN alone, and now we will mix them both. Crystal clear?
Yeah.
Beautiful. So in this case, we will do exactly the same as we did before. You know what? Let me get rid of these store variables because I don't want you to think that I'm faking it. So let me get rid of those. You can see that I cleaned them all. Let me clean the charts. Because to be honest with you, the mix of both will increase even more the accuracy, or at least that is the expectation. And that is something I wanted to show you. In real world, you do something. First, you go for regression to understand your data. Linear regression. Afterward, you perform a nonlinear regression to understand your transactions, how are behaving, whether are linear or nonlinear, and so on and so forth. Once that you have identified whether are linear or nonlinear, it's where actually you start playing with the classifications. And the classifications, you apply first one, which is KNN, afterward SVM, and last but not least, you apply them all or apply them both together. The one that gives you the most accuracy is the one that you need to use the most. So far, I think the highest accuracy that we have gotten so far has been 90.5%. Am I right? Top of mind, I think it's 90.5%. Okay, let's see what happens when we mix them.
Sorry, can you remind me really quickly where to look at that 90% easily? I forgot.
No worries. It's with the confusion matrix. With this one, actually, I'm removing all the variables. That is taking like forever. But if you remember, let
Yeah,
me.
you have to add the first and the last one, but is there a way to do it kind of more?
Yeah, just performing the confusion matrix. The
Okay.
confusion matrix is exactly the same. The only thing is that you sum out of the total, you perform the division of those accurate, those not accurate divided by those accurate, and that would be the
Okay.
accuracy.
Thank you.
You are welcome. I mean, it's kind of the fast approach, but let me see whether we can see that object here. So for instance, here we have the accurate where those that were predicted to not to be true and actually weren't true, 169. Those that were predicted to be true and actually went true, 83. So just sum them up, correct?
Okay, thank you.
So, however, the sum of all of them is 100%. Let me show you here in a formula. You know what? Let me show it in Excel. I think would be faster for everyone to understand the confusion matrix and how to evaluate that particular accuracy. I apologize, I don't feel quite well today. There you go. Okay, in here, let me show you in Excel. Perhaps that would be the fastest approach to show it. So for instance, we have the 0, 0, 1, 0, which is the combination of all of them. 0, 1. Usually in electronics is called the truth table, I think would be the translation. So everything that was predicted that were about to be false are 169. Those that were predicted to be true but were actually false, so that means an accuracy, 17. Those that were predicted to be false but actually went true, 11. And those that were predicted to be true that actually went true, 83. So if first we need to get the entire population, right? In order to get the entire population, we need to sum them all. So we need to sum. So the total population is 280, correct? So in order to get the accuracy, so out of the 280, we need to get how many were unsuccessful, which were equal to 17 plus 11. Those are the, let's put it here in F as fail. And those are actually went true will be equal to 169 plus 83, correct? So out of the population, those that actually, the percentage that weren't true will be equal to 28 divided by the total. So let me increase this. Where the dots in here? Around 1%. I'm sorry, around 10%. Apologies. And the other way around, right? It will be this one, which will be those that went true, were true predictions divided by the total, means will be the 90% remaining, correct? So in other words, what's the accuracy of our model? Those that went true?
90%.
90% accuracy, because those that were actually to be true, which were these ones against these ones, plus these ones, are the true predictions, which means 90% of our predictions are totally correct, which means the accuracy of our model is 90%. And guess what? Above 75% can be considered as very accurate model. And you might wonder, 70%? How come? Because if you bear in mind that when you are talking about experience, when you're talking about guts, and we are talking about um, your guess most of the time can be close to a flip coin. And in a flip coin, what's the probability that you get to be correct? What would be the probability?
50%.
50%. There you go. So whatever that it's above a 50% means that it's more accurate than luck. Does it make sense? However, to be honest with you, a model that is 70%, 70% accurate for me is not acceptable. For me, must be something above 80%. Why? Because it gives you kind of 20% bias to make a mistake. And that's the reason why I always aim to have 80% accuracy in my models. Does it clarify a little bit how the accuracy works?
Yes, thanks.
You are welcome. Now, let's take a look to the combination of both to see whether two models combined, how would those work? So in order to do that, actually, we have 17 minutes left. So in that case, well, you're familiarized with the process. So in that case, I may need to copy from the accordion that I have. I don't know how to say that in English, though. It's something I need to learn. Anyways, so, or maybe not, it is not important. So let me use that code in front of you because at the end of the day, you're familiarized with that code. So let's do the first thing, right? Explain step by step. Let's take whatever we already know that we need to take the data set. We read the data set and take only the meaningful columns for our sake. Now I need a volunteer. What are we doing here? What are we doing with these factors?
To create the category.
The category for those to identify which ones purchased the product and those ones that didn't, correct? Beautiful. So you understand what we are doing here. Now, we will invoke the CA tools, and now I need another volunteer about what we are doing here.
We are splitting into alternative values for data set.
Into alternative values. What do you mean about alternative values?
Not the full data set. It's used 40% of the samples.
Exactly.
Alternative.
Exactly. Beautiful. So we are using 40% of the data. Here I increased to 40%. In the past, I used 35%. In here, I'm using 40% to train my data to understand what's going on. And afterward, I'm using the remaining 60% to test my data, correct? It's exactly what we are doing. In here, we will perform the feature scaling one more time. Why? Because at the end of the day, we need to plot it. And in this case, we will mix both models, right? I told you about it. We will mix both models, which is the support vector machine and the KNN. So let's do that. In this case, let's invoke both libraries. In this case, both libraries, one of them was the class, which was for support vector machine, and the E1071, which was for KNN. Okay, so let's include them all. Now we will create an object, which is the Y prediction, which is going to be for the KNN, which is the nearest neighbors, correct? So in this case, as you can see, we are creating a Y pred, which the predictions will fall into this model. But despite the predictions will fall into this model, what we are doing, we are applying the model for that sample, the KNN, but aside of that, we will create a classifier. The classifier means we are classifying twice. Can you see that? That's why in this case, we are using the feature scaling. Because first, we are classifying using KNN first, and out of that classification, we will also apply the support vector machine. That's how we are mixing both models together. So good so far? Right? So let's run them both because I don't think I have run them. Let's see.
Just quick question. What did the 5 for K meant in the Y prep?
That's a very good question. The 5 means that we are planning to use it's a factor that you can test in order to improve the accuracy. In other words, how many inflections you will use in the model. So for instance, that's another way that we can increase the accuracy. In case that is not accurate enough, you can include a 6, but if it goes inaccurate, means that you need to decrease. It's a factor in order to the inflections that you can include to this chart.
Okay, thanks.
You are welcome. Because if you include one more, perhaps it will include this data point that looks kind of in the middle. If you include another inflection, it's what we're going to do. This is the way that you can increase the accuracy as well with the number of inflection that it has. K means how many inflections it will have. For instance, 1, 2, 3, 4, 5. These are the inflections that you're including as part of the model. That's a very good question. So good so far? So now let's run both objects in order to mix them both. First, apply the KNN, and afterward, include the support vector machine into one single model. So let's see how the accuracy increases.
I have a question.
Yes, please shoot.
How do you inject the first results to the second one?
How do you inject? So far we are not. So far we are only creating the objects. We have not mixed them. We have not mixed them yet until we perform the prediction.
Okay.
Yeah. So far we are only running the model separately, and we will mix them once that we are doing the results. Crystal clear?
Yes.
Beautiful. Okay, now it's still running, unfortunately. Has it run for anyone? I don't want, there you go. It finished, fortunately. So now it created two new objects, which is the classifier that it comes here, right? Which is saying, okay, the classifier includes a formula. Afterward, the widespread includes at the bottom, right? So we can see that are factors that, in this case, the classifier includes a list of 31 objects, and the widespread include a list of a classification for each one of them. The mix of both will be the final data. So in this case, now let's perform another prediction. So in this case, let's create the widespread. So we will override this object, right? So let's do, where we will use the predict method. And in here, we will use the classifier. So here we are mixing both objects together. Classifier. Am I missing one F? No, I think, yeah, it's right. And the new data, here we use the test set, test underscore set, and we will include them all, but the last column. So in here, let's perform the prediction maximum both. And now let's take a look to the confusion matrix. Let's call it a confusion matrix SV. What do you think? It will be more or less accurate? That would be interesting to see. Table, test set, and let's include all the rows and all the columns except the last one, and let's include the prediction. Let's take a look to that one. Yeah, here I may have a mistake. So
should it be just 3?
It will. You're totally right. Well, let's include. Yeah, we need to include the 3 columns. You're totally right. I'm sorry. Only the prediction, which is gonna be the 0, 1, 0, 1. You're right. And let's include all the objects. Now let's take a look. What would be the accuracy? Hopefully, crossing fingers, would be better. Confusion matrix, and we call it SV. Let's take a look. Now we have 203 against 37. I think it's more accurate, right? Last one we have 100, 203, but let's take a look. Let's take a look to the formula. So it will be, so the total population would be 140. Actually, let's use Excel. Let's take a look. Here we have everything, right? So now we have, oh, actually 140 actually was less accurate. We have 23. Yeah, it was less accurate. I didn't expect it. I didn't see it coming. So that's exactly what I want to show you. That's why you need to use all the models all together. Because I was expecting, as per mixing both, I was expecting it to be more accurate, but guess what? That's why you need to test them all. Because sometimes one of them would be more accurate, or you need to clean up your data more. Those are the tough decisions that the data scientists need to take on daily basis. Because at the end of the day, you need to decide which model is more accurate based on the results, not based on your assumptions. However, if you want to increase the accuracy, maybe we need to include here the number of Ks. Let's see whether we include a 6 more, what happens? I'm sorry, someone has a question? Claudia, go ahead.
Because sorry, but I cannot see where you mix both, because you are overwriting the values for widespread with the prediction about classifier.
Yes.
But when or where you are mixing both?
Technically, here in this object, if you take a look, here we're taking the widespread, right? So we're taking the classifier, which is SVM, and here we're taking the new data, that is the test data that came out of the out of this data, right?
Yes,
so,
it's just the escalation.
You're totally right. Here we are not mixing the models. We are taking only the last classifier in here. In order to do that, then in that case, we need to include the widespread in here. You are totally right. Let's see how it goes here.
Okay.
We need to scale that one. We need to scale that one. So we need to perform widespread scale.
Widespread just have the value about prediction, right? It's just
About the
one
prediction.
column. It's just one column.
No, it's actually a probability. Actually, let's take a look to that one. Look at that. As you can see, it created the two, it has two levels, which are the two factors, which is the prediction. You are totally right. So in this case, we may need, here we have the prediction. So in order to perform the mix of both, we may need to create alone each and one of them, scale them both, and include it into a single model. You are totally right. Actually, this model is not mixing both. We are only testing them isolated. Thank you so much for that clarification. Actually, you are totally right. Because in here, we're performing the widespread for the KNN, and we may need to mix them both, but change this classification to use the outcome of this prediction within this classifier in order to make sure that we can test it. But you are right. So I think I'll create a video about for you, all of you, about how to mix it in order to make sure that we can mix them both.
Okay, thank you.
But that's a very good observation. Thank you so much. So is there any question so far, perhaps that you may have so far, or maybe for the final assignment for the last 4 minutes that we have together?
No.
Is there any question? Comment. Do you find it useful, the classification models, and how you can use them, and how you can explore different data in order to identify who's going to be your high-end customers and low-end customers? And actually, in the next class, here we have some categories, or we have some idea about how to classify the data. Next class, we'll take a look about how to classify something that we have no idea how to classify it, which is going to be clustering, which based on the different methods, let's say that you work for sales, right? You are a sales manager and you have certain groups of customers and you only have 3 sales consultants. So each and one of them has a different skill set, correct? Some of them may be better for sales. Some others may be a little bit less skilled, right, for selling. So based on that, if you have identified, you can classify them. You can classify your salespeople and identify which one is better for selling, which one requires more training. And based on that, you can classify your customers and say, you know what, those that are actually high end, I'm gonna assign them to my best seller. Those that are actually lower end, I will apply them, or I can assign them to my lower seller level. And those in the middle can be, of course, for the middle seller. In case you have more salespeople, you can create more groups, which actually is going to be the K for the clusters. It's going to be, depending upon how many groups you need to create, you can change the K in order to perform the classifications automatically on despite you don't have an idea about how to classify it. But that's going to be for next class. It's called clustering. Please take a look to the documentation that we have available for you so you can read ahead on time, because clustering requires some mathematical mindset as well, because we use the centroid method for the k-means clustering, which means out of the entire dataset, if you want to classify into X number of groups, you use the centroid method. And the centroid method, what it does, it creates a point in the middle of the entire chart and creates the first group. If you want 2 groups, it creates, based on the distance of all the points, it creates 2 points and creates 2 groups. If you want 3 groups, it creates 3 points out of the entire dataset, but everything is being made automatically. Something that you don't have to do as I did here in the Excel, right? Because, I'm sorry, in the PowerPoint. Oh my God, here in the paintbrush. In the paintbrush, if you remember, I did it kind of top of mind, right? However, the clustering will do it automatically. If you say, you know what, Mr. Cluster, I want only 1 group. The cluster will identify the group immediately, right? This is straightforward. But what if I asked the cluster to create 5 groups? That overcomplicates things, right? Because out of here, how would you classify them? Well, top of mind, I can say, well, this is 1 group, another group, another group, another group, and another group. However, I am unsure whether that is correct. So the algorithm, what it's going to do, it will create, based on the equidistance of all the points in the entire data set, it will create the most accurate groups depending upon the different statistical factors, and it would give you an output about what the suggestion for the classification. That's what's going to take a look to the next class. So in other words, it performs the classification when you don't have categories or you don't have kind of an idea about how to classify things. So thank you so much, everybody. Either way, I'll send you the video about how to mix the both codes together, because that's a very good point that your partner mentioned about. It's something that I'm going to include as part of the model in order to test one model, apply for the next model, and get a final output. Is there any questions so far? If there are no further questions, thank you so much, everyone. Have a wonderful evening. See you on Tuesday.
Thank
And
you,
those who actually
teacher.
have questions, you
Bye.
you
Thank
are
you.
welcome. Have a wonderful evening. Take care.
Bye. Take care.
Take care. Thank you so